Seismic activity has recently increased at Mount Rainier, a glacier-capped stratovolcano located in the state of Washington, United States. Despite this uptick in earthquake frequency, the volcano remains at a green or normal status level, indicating no immediate signs of eruptive behavior. Over 200 earthquakes have been recorded in the latest swarm, most of which began occurring late last night. While the U.S. Geological Survey, USGS, officially reports around 221 events, the actual number continues to climb. These tremors are relatively small in magnitude, with the strongest registering only a magnitude 2.1. Importantly, they are also very shallow, located just beneath the volcano's summit, far above the depth of the known magma chamber, which lies approximately 5 miles or 8 kilometers below the surface. Such shallow seismicity suggests a process unrelated to magma ascent. If molten rock were actively rising toward the surface, the seismic signatures would be more intense, frequent, and likely originate at greater depths. Instead, experts suggest the likely cause of the current swarm involves crystallizing magma that is interacting with fluids within the subsurface fault zones. These fluids can reduce the friction between opposing blocks of rock, making it easier for them to slip past each other and trigger earthquakes. This phenomenon resembles a similar seismic swarm observed at Mount Rainier in 2009. Though not unprecedented, this level of activity has drawn renewed attention due to the potential implications for the surrounding heavily populated areas, including cities like Seattle and Olympia. The primary hazards in the event of a future eruption would include massive mud flows or lahars, rather than widespread lava flows or explosive pyroclastic activity. Mount Rainier's heavily glaciated slopes make it especially prone to these destructive, fast-moving torrents. It's also worth noting that no signs of ground deformation, such as surface inflation, have been detected via GPS monitoring, an important indicator typically observed before volcanic eruptions, such as those frequently seen at Kilauea in Hawaii. The absence of this type of data reinforces the current interpretation. While the earthquake swarm is scientifically significant and worthy of continued observation, it does not yet suggest magma is on the move toward the surface. Seismic data from a nearby monitoring station reveals that the region has experienced well over 200 earthquakes so far. These readings, captured from a single seismograph, suggest a persistent swarm of minor tremors, some of which have increased slightly in magnitude earlier today. The latest charts confirm that the activity continues even now. Monitoring efforts include not just seismographs, but also GPS stations positioned around the volcano to detect ground deformation. Although one of the GPS units appears to be offline, others are still functioning and provide long-term data critical to interpreting volcanic behavior. One such station tracks horizontal movements both eastward and northward, as well as vertical displacement, which is especially important in identifying inflation that could signal magma movement beneath the surface. The records from this GPS station date back to August 2020 and offer a clear picture of the past 5 years. The observed changes fall within normal seasonal variation, likely influenced by annual snowmelt, and show no unusual upward trend that would indicate volcanic inflation. The movements recorded are extremely subtle, in the range of 0.0005 meters or 5 millimeters, which is considered minimal and not indicative of magmatic intrusion. Based on this data, there is currently no evidence to suggest that magma is ascending toward the surface. The long-term patterns are stable, and recent activity aligns with what has been recorded over the past several years. While it is true that this volcano has not erupted in roughly 1,000 years and will inevitably erupt again at some point in the future, there is no current sign of imminent volcanic activity. The earthquakes being observed are likely the result of very shallow crustal processes rather than deep magmatic movement. According to research published in 2022, this kind of seismicity can occur due to interactions involving crystallizing magma beneath the crust. While the article in question focused on Yellowstone National Park, the mechanisms it describes are relevant here as well. Today, the United States Geological Survey, USGS, released an update confirming that the volcano remains at green alert level, indicating normal background activity. Mount Rainier has a long and complex seismic history, punctuated by events that highlight the tremendous forces deep beneath its surface. One particularly notable occurrence was the magnitude 4.5 earthquake that struck on the evening of October 7th, 2006, at 7:48 in the evening local time. This was the strongest earthquake recorded in the area since the year 2000 and originated just about 1 mile or 1.6 kilometers beneath the surface. Although it was not a sign of imminent volcanic eruption, it underscored the volatile dynamics within the mountain's interior. Every tremor, no matter how subtle, reveals a fraction of the tension and pressure that continues to build, a silent warning of the potential for future transformation. Contrary to popular imagery often associated with volcanic eruptions, Mount Rainier does not primarily threaten the region with rivers of lava. Any molten rock produced would most likely remain confined within the boundaries of the national park. Likewise, while volcanic ash would pose hazards, prevailing wind patterns would likely carry it eastward, away from the densely populated urban centres to the west. The true danger, as identified by the United States Geological Survey, lies in the possibility of LAHARs. These are violent torrents of water mixed with volcanic debris and sediment, capable of forming when an eruption rapidly melts the mountain's vast glacier system. Such flows can charge down river valleys with enormous force, sweeping away forests, buildings, roads, and entire communities. Rising to over 14,400 feet, or approximately 4,390 meters, Mount Rainier is among the tallest and most heavily glaciated peaks in the lower 48 states. Its towering elevation and massive ice reserves create ideal conditions for lahars that can travel at frightening velocities. Experts from the USGS Cascades Volcano Observatory have emphasized this threat. Research seismologist Seth Moran explained that the combination of Rainier's height and ice coverage means an eruption could unleash a surge of meltwater and debris almost instantaneously. For those living in the valleys below, this could mean disaster with very little time to escape. Lahars have the potential to travel at speeds of up to 50 miles per hour or about 80 kilometers per hour. These surging flows have the power to uproot trees, destroy infrastructure, and bury entire towns under thick layers of mud and rock. They can travel more than 50 miles or 80 kilometers from their source. One of the most destructive examples in the volcano's history is the Osceola mudflow, which occurred roughly 5,600 years ago. It spread across more than 200 square miles, or over 500 square kilometers, leaving permanent scars on the landscape. If a similar event were to happen now, it could devastate communities like Orting, Sumner, Puyallup, and parts of Tacoma, where tens of thousands of people currently live within mapped lahar zones. In some cases, these areas could be reached in as little as 30 minutes, making timely evacuation nearly impossible without advanced warning systems and rapid response measures. The consequences could be overwhelming if preparedness fails. Adding to the potential devastation are pyroclastic flows, which present a separate but equally terrifying hazard. These fast-moving avalanches of superheated gas, volcanic ash and rock can exceed temperatures of 1,000 degrees Fahrenheit or about 540 degrees Celsius and move faster than 300 miles per hour or 480 kilometers per hour. The energy released during such flows rivals that of multiple nuclear explosions. While these deadly surges are expected to remain within a 10 to 15 mile or 16 to 24 kilometer radius of the summit, they pose a severe risk to anyone near the crater, including climbers, scientists and tourists. More critically, the intense heat from pyroclastic flows could instantly melt Rainier's glaciers, triggering lahars that would surge down into populated valleys, magnifying the scale of destruction in moments. Volcanic ashfall poses a serious danger that extends far beyond the immediate vicinity of an eruption. When a volcano like Mount Rainier erupts, it can propel immense columns of ash several miles or kilometers into the sky, dispersing fine, abrasive particles across vast areas. Communities throughout the Pacific Northwest, including cities as distant as Seattle and Tacoma, located within approximately 50 miles or 80 kilometers of the volcano, could be blanketed in thick ash. Such fallout can trigger a cascade of public health emergencies, as the ash irritates respiratory systems, particularly among vulnerable populations. Roofs may collapse under its weight, flights could be grounded due to reduced visibility and engine damage risk, and roads might become impassable. Depending on prevailing wind patterns, the ash could travel hundreds of miles or kilometers, contaminating reservoirs and rivers and threatening both drinking water supplies and irrigation systems. In regions like eastern Washington, Idaho and Oregon, farms could be severely affected, with crops smothered and livestock exposed to hazardous particulates. In such a scenario, power outages would likely follow, and long-term health consequences could burden communities for years. Though lava flows from Mount Rainier are less far-reaching than those from shield volcanoes such as those in Hawaii, they remain a dangerous aspect of its eruptive potential. The lava here is significantly more viscous, limiting its spread to just a few miles or kilometers from the summit. However, the slow advance of such lava can still obliterate infrastructure and poses an indirect threat by melting glacial ice and snow. This sudden melting could generate massive mud flows known as LAHARs, capable of sweeping down the mountain at terrifying speeds, dragging debris and destruction through valleys and towns below. Another ever-present danger comes from the instability of the mountain's steep flanks. Even in the absence of volcanic activity, Mount Rainier's slopes are prone to landslides and earthquakes. A strong seismic event could dislodge enormous volumes of rock and glacial ice, generating landslides that evolve rapidly into fast-moving lahars. These flows can travel many miles or kilometers through river valleys, swallowing bridges, highways and entire communities in a torrent of mud and debris. The Puyallup, Nisqually and Carbon River valleys, densely populated and economically vital, are especially vulnerable, where thousands of lives and homes remain exposed to the mountain's latent instability. Historical events offer chilling precedent. In 1985, Colombia's Nevado del Ruiz erupted, melting its glaciers and sending a massive lahar cascading down toward the town of Armero. Within mere hours, over 23,000 people were killed. The mud, thick as wet cement, buried everything it touched. Volcanologist Bradley Pitcher described the aftermath as a scene of irreversible entrapment, likening the lahar to a deadly quicksand from which nothing could escape. Mount Rainier harbours an even greater threat, containing nearly 8 times more glacial ice than Nevado del Ruiz. Should a similar event occur here, the resulting lahars could wipe out entire communities in minutes, leaving behind scenes of devastation unmatched in the continental United States. According to the latest US Geological Survey threat assessment, Mount Rainier ranks as the third most dangerous volcano in the country, surpassed only by Kilauea in Hawaii and Mount St. Helens in Washington. The long-term consequences of a major eruption would ripple far beyond the mountain's shadow. Infrastructure crucial to commerce and emergency response could be destroyed, roads, rail lines and bridges severed, isolating populations and delaying aid. Among the most at-risk assets is the port of Tacoma, a cornerstone of trade in the region and located directly within a high-risk lahar zone. Its loss would not only paralyze regional supply chains, but also reverberate across national and international markets, triggering economic consequences on a global scale. The aftermath of volcanic ash dispersal would introduce another layer of devastation. Dense ash clouds could immobilize air travel for extended periods, much like the 2010 eruption of Geological in Iceland, which grounded flights globally and stranded millions. Ash and debris infiltrating rivers and reservoirs could compromise water quality, depriving countless individuals of safe drinking sources. Agricultural systems, a vital component of the regional economy, would be left in disarray. Farmlands may be suffocated beneath ash deposits, and formerly arable soil could become infertile for extended periods, threatening food supply chains and driving many farmers into financial collapse. If Mount Rainier were to erupt with the force observed in its geological past, or produce an event rivaling the 1980 eruption of Mount St. Helens, the consequences would be catastrophic. The death toll could reach tens of thousands, especially if a large lahar surged down the slopes with little warning. Communities in its path might be erased, and the financial impact could exceed 10 billion USD, leaving behind a crippled economy, fractured infrastructure, and displaced populations. Such a scenario reinforces why Mount Rainier is considered one of the most dangerous volcanoes in the United States. Advanced simulations have attempted to assess the consequences of a lahar cascading down the mountain's western flanks. One projected outcome modeled the release of approximately 260 million cubic meters of volcanic debris, the equivalent of over 104,000 Olympic-sized swimming pools. Traveling at an estimated velocity of 4 meters per second, or about 13 feet per second, the flow could reach the town of Orting, Washington, in less than an hour, destroying everything in its path. The Nisqually River Valley also poses significant risk. Should a lahar reach Alder Lake, the resulting surge could exert extreme pressure on the 100-meter or 330-foot-tall Alder Dam. A potential failure of the dam could lead to devastating downstream flooding, amplifying the destruction far beyond the volcano's immediate surroundings. The threat posed by Mount Rainier is not limited to eruptive activity. The mountain's underlying geological processes are volatile and largely unpredictable, capable of transforming entire landscapes with little notice. Yet, despite this latent peril, Rainier captivates with its natural grandeur, glaciers etching deep ravines into its slopes and evergreen forests thriving at its base. It remains a place where tranquility coexists with peril, embodying both the beauty and brutality of Earth's dynamic systems. To the scientific community, Rainier represents a profound challenge, an ever-shifting terrain of glacial movement, concealed magma channels, and fault lines waiting to rupture. It offers rare opportunities to understand planetary behavior, while consistently eluding exact forecasts of its next awakening. For nearby communities, the volcano is a symbol of identity and awe, yet also a lingering threat. Preparedness efforts include early alert systems, detailed hazard assessments, and coordinated evacuation routes, all developed in the hope that when the inevitable occurs, lives can be spared. Meanwhile, Mount Rainier looms above the horizon, its ice-covered summit a stark reminder of the fragile relationship between human existence and the untamed forces of the natural world. The likelihood of Mount Rainier setting off a chain reaction among other volcanoes in the Cascade Range remains extremely remote. Although these volcanic giants share a tectonic birthplace within the Cascadia subduction zone, they operate in isolation from one another. Each volcano maintains its own subterranean architecture, with separate magma chambers, unique stress regimes, and individualized plumbing systems that drive activity based on local geological conditions rather than direct influence from neighboring peaks. The Cascadia subduction zone itself is an immense convergent boundary stretching along the Pacific Northwest, where the Juan de Fuca Plate is steadily diving beneath the North American Plate. As this oceanic plate descends deep into the Earth, rising heat and intense pressure force water and volatile elements from the subducted slab to escape into the overlying mantle. This influx of fluids reduces the melting point of mantle rocks, generating magma that rises slowly through the crust, forming the Cascade volcanic arc. Yet despite sharing this tectonic engine, each volcano responds to its own set of geological variables, including differences in crustal structure, magma chemistry, and internal pressure buildup. Mount Rainier exemplifies this independence. Its magma is rich in silica, which makes it significantly more viscous than the magma found in some other Cascade volcanoes. This thick magma resists flow, allowing pressure to accumulate more readily, setting the stage for explosive eruptions. Beneath the surface lies a magma chamber that varies in shape, size and depth, all of which influence how and when the volcano might erupt. As magma fills this reservoir, gases such as water vapor, carbon dioxide, and sulfur dioxide become trapped. Over time, these gases increase the internal pressure. When that pressure surpasses the strength of the surrounding rock, fractures can form, giving magma a path to escape. The crust surrounding each volcano adds another layer of complexity. Past eruptions, tectonic forces, and the weight of overlying rock create stress fields that determine how and where magma may travel. In the case of Mount Rainier, the heavy presence of glacial ice adds a dynamic pressure load that can shift over time due to seasonal melting or climate change, subtly altering stress patterns within the crust. These fluctuations can affect the timing and behavior of magma movement beneath the volcano. Moreover, the expanding gases within silica-rich magma systems like Rainier's act as powerful eruption triggers. As magma ascends, these gases expand dramatically, amplifying the pressure and increasing the chances of a sudden violent eruption. Although one volcano's eruption in the Cascades is unlikely to directly cause another to erupt, indirect effects cannot be entirely dismissed. A powerful eruption produces seismic waves that ripple through the Earth's crust, potentially changing stress conditions in nearby volcanic systems. Mount St. Helens' dramatic eruption in 1980, for instance, was accompanied by widespread seismicity that temporarily influenced surrounding regions. In rare cases, these disturbances may shift underground fluid systems, hydrothermal networks of heated water and gas that help regulate volcanic behavior. If a nearby volcano were already approaching a critical state, such a disruption could theoretically hasten an eruption. Still, this kind of chain reaction remains exceedingly rare, and would almost certainly require pre-existing instability in the second volcano's system. Despite being shaped by the same tectonic forces within the Cascadia subduction zone, each volcano in the Cascade Range operates as an independent and unpredictable system. Mount Rainier in particular poses a significant threat not because it might trigger other eruptions, but due to its own capacity to generate devastating lahars, searing pyroclastic flows and widespread ashfall, all of which could endanger the densely populated regions surrounding it. As scientists from the United States Geological Survey continue to monitor the mountain's behavior with precision instruments and real-time data, one fact remains clear: being prepared can make the difference between survival and disaster. Whether current unrest is a fleeting anomaly or an early signal of something more dangerous, the mountain's long and restless history shows that dramatic changes often arrive without advance notice. Public awareness and readiness are crucial. If Mount Rainier begins to awaken, the question is not if the warning signs will be detected, but whether communities will be ready to respond. Continued observation and timely communication remain essential as this situation evolves. If you found this video insightful, don't forget to like, share and subscribe for more updates on volcanic activity, natural disasters and breaking science stories. And make sure to hit the notification bell so you're the first to know when new content drops. Stay safe, stay curious, and we'll see you in the next video.